I want to begin by making a few more remarks about the RSK algorithm that you have seen already in a previous video. So the form of the RSK that you have seen there is via this Shenstead's insertion algorithm. Now here's an important sort of variant, if you wish, of this, which is called the dual Shenstead insertion. Okay, this is, think of it as a slight variation of the previous insertion algorithm. So let's just do this by example. So it's easiest to understand how to do this by just working out a example here. So what we do is, as before, we process a word and convert it into a tableau of certain kinds. So for example, if you have 3, 4, 1, 1, 2, 3, 1, 2 is a word. Okay, now we are going to read this word one by one and start forming tableau out of this. Okay, so the initial process is a bit like usual insertion. So I see the 3 first. So the 3 just stays by itself. So that's a new box, the young tableau. So I keep track of it by saying, okay, so that's my so okay, let's come back to the boxes, the recording tableau afterwards. So let me just see how to do the insertion bit at least for a start. So then I look at 4 now. Okay, now the 4 comes along and, well, it just stays to the right of 3. Okay, because 3, 4, I mean, it's in the right order. Okay, now something interesting happens. The 1 is read next. So I try to insert the 1 into this tableau. Now where does the 1 fit? Well, there's only one obvious place for it. So the 1 goes in and bumps the 3 out. Okay, so let's do that. Let me erase the 3. So maybe we'll just write all the steps out. So why let's not erase. So let me just keep track of every step of the algorithm, so it's clear what bumped what out and so on. Okay, good. So let's look at this. So 3 came in first. Step 2, 4 came in. So I just got 3, 4. Now the 1 came in and it bumped the 3 out. Okay, so the 3 went down to the next row. Okay, so this is, so far it is like the usual insertion. Now something new happens, okay, in the dual insertion algorithm, which is the following, that we read a 1 again. Okay, now the rule here is the following. When you try to insert a 1, what the 1 does is it sort of moves all the way till it finds anything that's greater than or equal to itself. Okay, so this is different from the usual insertion where you sort of scan that row and see if you can find something greater than that number that you're trying to insert. In this case, we look for anything that's either greater or equal to itself. So in this case, it finds a 1. Okay, so you find sort of the last guy, the leftmost number which is greater than or equal to this 1. Okay, and you bump that guy out. So this new 1 takes the place of that 1. Okay, 3, and now this 1 gets bumped out. Okay, so now I look at it in the second row and try to insert it into the second row. Now how does that work? Well, again, this 1 looks at the second row and it finds, well, there's only a 3 which is greater than or equal to itself. It bumps the 3 out. Okay, so here's what happens. So this 1 goes into the second row, bumps the 3 out. Okay, so that's what happens in the second step. Okay, now when you read the next one. Okay, then we read the 2. Now what happens to the 2? So again, the 2 tries to enter the first row and the only thing it can bump out is the 4. So the 2 takes the place of 4. The 4 goes to the next row and, well, it can fit right next to the 1. So this is what happens to the next step. Now let's look at the 3 here. Let's go down. The 3 tries to enter the picture and, well, it has no trouble. It just fits into the first row. Now the 1 comes in next. So again, recall what the algorithm was. The 1 comes in and it looks for anything that's either equal to it or greater than or equal to it, and finds the leftmost such element. In this case, there's only one such element, the 1 itself. So the new 1 which comes in bumps out the old one. Okay, so what happens? So I have 1, 2, 3, I have 1, 4, right? That's the new one which is sort of come in here. Now the old one that was here. Okay, so this new one, maybe we'll put it in yellow. The new one was the guy which tried to enter this in yellow. That goes and takes the place of the old one. So the old one gets bumped out and it tries to enter the second row. Well, again it bumps this one out. Okay, so this new one takes the place of the old one and bumps that one out. So I had a 3 already. So it's like sort of successive bumping outs of 1. So this one goes and takes the place of that one, and the 1 gets bumped out. Okay, now what will this new 1 do? It will go and bump the 3 out. Okay, it takes its place in the third row. It bumps the 3 out and does this. Okay, so this is what you're going to get after you have read the 3. After you have read this 1. Then finally you read a 2. Okay, that's, well, what's that going to do? That 2 similarly, recall what will the 2 do? It will sort of look here and find anything bigger than or equal to it. It finds this guy, this 2, and it bumps that out. So the new 2 goes in and bumps the old 2 out. Okay, that old 2 will try to enter the second row. Where can it enter? Well, by bumping the 4 out. So this 4 gets bumped out. 2 goes in, 4 goes to the next row. Okay, and now in the next row there's already nicely space for this 4. The 4 just goes and fits there. So that's the final result of this bumping algorithm. Okay, so the difference now really is that the greater than or equal to rather than the greater than. Okay, now you are probably already a little worried about this, because contrary to what we got in the usual bumping, the dual bumping algorithm doesn't seem to produce a tableau, right? Because a semi-standard tableau was supposed to have entries increasing strictly along its columns. But here what you have are entries which are, well, only weakly increasing. Okay, but something interesting has happened. The rows are strictly increasing. So observe, in this case, the rows are strictly increasing, whereas the columns are weakly increasing. Okay, so what you're getting is really sort of a dual tableau with rows and columns interchanged. But instead of sort of giving it a new name, the easiest thing one can do is to say, well, instead of taking this, let me just do the following. Let me just transpose this tableau. In other words, I will interchange the role of rows and columns. I will write my first column as a first row, second column as the second row, third column as a third row. And when I do this, what I get is in fact an ordinary tableau, semi-standard. It's weakly increasing along rows and strictly along columns. The only thing that's happened is that if this had some shape lambda, right, the rows and columns got interchanged, the shape of this new partition is the transposed shape of the original. Okay, so in order to get the semi-standardness, we need to transpose the shape. So you get something semi-standard but of shape lambda prime. So that's one way of thinking about what this dual algorithm does, the dual insertion. It takes a word and finally it produces. So this is the final end product is what we think of it as producing. This is the output. It's a tableau of some shape. Okay, the shape is dual to what we got in the one step before it. Okay, but now this is just for a word, but if you recall how the usual RSK worked, you can associate, you can perform the algorithm starting with a matrix with non-negative integer entries, right? Now here there is again a matrix version of this, which is what we'll be interested in. So what's the dual RSK? It's the following. It's a bijection, if you wish, between matrices. So between, on the one hand, 0, 1 matrices. So the set of 0, 1 matrices. So take the set of all 0, 1 matrices on the one hand. The dual RSK, you can think of it as a algorithmic bijection, which associates to a 0, 1 matrix. So a 0, 1 matrix is just a matrix all of whose entries are zeros or ones. To such a matrix, it associates a pair of tableau. Okay, let's again call it P and Q. So P tableau and Q tableau, with the following property that the type of P. So the type of P is nothing but the column sums of this matrix A. Okay, so I should say, given a 0, 1 matrix A, it associates to it a pair PQ. So let's maybe remove all the sets. So suppose I have a 0, 1 matrix A. So here is an algorithmic definition, if you wish. What does the dual RSK do? It associates to it a pair PQ of tableau. So where the P and Q are semi-standard tableau of dual shapes. Okay, so P, Q are both semi-standard Young tableau with the following property that the shapes of P and Q are dual to each other, are transposes of each other, so such that shape of P equals shape of Q transpose, and the types of P, okay, and the type of P is exactly the column sums of the matrix A, and the type of Q turns out to be the row sums of A. Okay, and the key point here is that it is a bijection from the set of all 0, 1 matrices to the set of all pairs PQ of semi-standard Young tableau of dual shapes. Okay, so the additional property that it satisfies is this, that the row and column sums of the matrix A are related to the types of P and Q. Okay, so rather than repeating sort of a proof which is analogous to the proof for just the usual RSK, let's just do an example. Okay, so let's just see this by example. I haven't told you how to get the tableau Q, but that's the same recording tableau process that one has in the usual RSK. Okay, so let's take a matrix A with just zeros and ones in it. So for example, 1, 0, 1, 1, 1, 0, 1, 0, 1. Okay, so here's a matrix A. Now, if you recall how the usual RSK works, we convert this into what we sometimes call a by-word, okay, which is just a word in which we note down the locations of the ones, okay, the row and the column. So for example, this matrix has the 1th entry has a 1, so I remember that as 1, 1, and this is the first row, third entry, 1, 3 is a 1. This is second row, first entry, second row, second entry, third row, first entry, third row, third entry. So I note down, essentially I encode the set of locations in the matrix which have ones in them. Now, having done this, what I do is the following. I just look at this bottom row, and now I perform dual insertion to it. Okay, I don't perform the normal insertion, I perform the dual insertion. Okay, now while performing the dual insertion, I will also record my moves and fill in the values in the top row. Okay, exactly analogous to the usual RSK. So let's do this. So how will we do dual insertion to the word 1, 3, 1, 2 and 3? So first I get a 1, then I read the 3 and the 3 goes here. So the first box that I added was where the 1 appeared, and then the next box was where the 3 appeared. Now So corresponding to that, the first two boxes, so the first box should correspond to this, the second box has the, when I record it, I'll put the ones there. Okay, now let's look at what the next box would be. So I have to continue with the insertion. So I see a 1 coming in. Now the 1, if you remember, it goes in and it bumps this 1 out. Okay, so this is where I am after 3 steps of the insertion. So this bottom box here is the one that has been newly added, and I should fill the 2 there. That's the third element of the top row. Okay, then let's see what the insertion will do next. I see a 2 coming in. What will the 2 do? It will bump the 3 out, right? So the 2 that comes in bumps this 3 out, and the 3 moves to the next row. Okay, thereby adding this additional box, and in that box I will fill whatever the next entry is, which is a 2. Now finally I need a 1 again. So what will the 1 do? The 1 comes in, it bumps this 1 out, which goes to the next row, which goes in, bumps this 1 out, which goes to the next row, and it sort of goes and lies there. In other words, this was the new box that's created, which should be filled with this number 3. Finally, I have the number 3 coming in, which just goes and sits right there. So that's where my new number 3 new box is, and that box corresponds to this number. Okay, so I in some sense this is my Q tableau, which records the new boxes that were created at every step of the bumping algorithm. And what you see on the left is really the result of the bumping itself, right? This is the result of the dual Shenstead bumping, except if you remember I said this is not quite semi-standard. So what we do is we convert this into a semi-standard tableau by just taking the transpose. So I should change this to 1 1 1 first row, second row is 2 3, and the third row is a 3. Okay, this is now a semi-standard tableau. So this guy I'll call P. Okay, now observe that these are actually conjugate shapes. Okay, I mean in this case P and P conjugate are actually the same, but if you see what I did in just the one penultimate step, this at this point the shape that I get is the same as the shape of the recording tableau, right? The recording tableau is just keeping track of what the shape is at every step of the bumping. But the very last step is when I take the transpose of the original matrix. So in general, I mean in this case they are the same, the transpose and the original shapes, but P will be the transpose shape of the penultimate step shape. In other words, P will be the transpose of the shape of Q. So in general, shape of P will be shape of Q transpose. Okay. And observe the type, that's also easy to see, because how many 1s, 2s and 3s are you going to have in P and Q? Well, I'll have 3 1s, 1 2 and 2 3s in P. Okay, where does that come from? I have 3 1s, that's in the bottom row of this byword. I have 1 2 and 2 3s. Right? Those are the entries in P. Now the entries in Q were the entries similarly of the top row of this byword. Okay, so if you see how many 1s will I get in Q, well, that is just telling me, you know, the top row, remember, was keeping track of the row coordinates. The 1 1 that you're seeing here keeps track of the fact that there are 2 1s in the first row. Okay, so the row sums, the sum of the 1s in the first row just tells me how many 1s I'm going to get. Similarly, the number of 2s I get, these two 1s tell me that there are 2 2s that should occur. Similarly, 2 3s correspond to having these 2 1s. Okay, and then likewise the column sums. So for instance, why do you have 3 1s in the bottom row? Because there are actually 3 1s in the first column, right? They are the ones which contribute to the 1s in the column, and so on. Okay, so I'm just sort of going over this fast because you've already seen this in the context of the usual RSK. Okay, good. So what this finally does, the dual RSK then, is it maps a 0 1 matrix. Okay, so the key point here, I mean there's something that I haven't said too carefully, which is that if this is a 0 1 matrix, only then are you going to get you're going to get semi-standard tableau in this case. Okay, so the dual insertion has this this property that you will get semi-standard tableau that you will get semi-standard tableau for both P and Q. I mean, P of course is going to be semi-standard, but why is Q semi-standard? That's the point. Okay, and that is ensured by the fact that the original matrix you started out with only has zeros and ones. Okay, otherwise Q may not end up being semi-standard. Okay, good. So this is the dual RSK. And one more remark that I wanted to make about just the usual RSK is the symmetry property. Okay, so this is the usual RSK algorithm itself, which is you take a matrix A, right? This is just a non-negative integer matrix, and to that you associate a pair of semi-standard tableau of the same shape. So this is the usual RSK, not the dual RSK. The shapes are the same. Okay, and it's a bijection from set of all integer matrices to semi-standard tableau of the same shape. Okay, with the additional property that the row and the column sums of A are exactly the types of Q and P. Okay, now there is a nice symmetry property here, which is that what interchanges rows and columns? Well, the operation of transpose. So if instead of the matrix A, I look at the transpose of the matrix A, and then ask, well, what is the image of A transpose under the RSK map? It turns out beautifully to be just the pair Q comma P instead of P comma Q. Okay, and this is somewhat unexpected but very beautiful fact. So what does this mean? In particular, it says that as a corollary, if A is symmetric, in other words, A is equal to its transpose, then under the RSK map, P equals Q. Right? Because there are two different ways. You think of A as A or as A transpose. In one case you get PQ, in the other case you get QP, but they must be the same. So what this means is that the two things P and Q are actually equal if A is a symmetric matrix. And you can again think of this as a bijection from the space of symmetric integer, non-negative integer matrices to the set of, P comma P is just P, right? So I forget about the pair PP, I just map it to P itself. So there is actually sort of as a corollary, if you wish, of this RSK, just the usual RSK. It says that if I take the space of all symmetric integer matrices, okay, from this space there is a bijection to just semi-standard Young tableau. Okay, now the symmetric matrices of some size, any size really. Okay, and the key property here is that the row sums and the row and the column sums are equal because it's a symmetric matrix. The row sum of the given matrix will just map to the type of the semi-standard Young tableau. Okay, so this is the symmetry property. And why are we interested in this? Well, of course, for us, if you recall, this RSK was something that we used when trying to look at monomial expansions. Okay, so let's just so in this context of symmetric functions in infinitely many variables, let's just define the same notions that we had before, which is that of the elementary symmetric functions and the complete homogeneous symmetric functions. So here's my definition. How will I define En for any n, or Ed maybe? So how should I define Ed in the infinitely many variables x? Well, it's just the monomial symmetric function corresponding to 1, 1, 1 d times. In other words, it's just I take xi1, xi2, xid, just products of d tuples of the xi's Okay, summed over all possibilities. So this is the obvious definition for the elementary symmetric function. Now what's the complete homogeneous symmetric function of degree d? Well, as before, it's just a set of all monomials of degree d. Take all monomials corresponding to partitions of d, and I take all possible monomials, I sum them all up. Or in other words, I take the sum of all the monomial symmetric functions corresponding to partitions of d. That's my hd of x. Okay, and if you recall how we define the more general versions, so if I want to talk about E lambda of x, okay, how do I define this? Well, this is just a product of the E lambda 1, E lambda 2, E lambda L. Similarly, H lambda of x. Where what is lambda? Lambda is some partition with L parts. So given a partition, I can talk about E lambda and H lambda as before. Okay, and you know we've done this in the case of finitely many variables. The definitions are more or less the same, and the key lemma there, or the key proposition there, which has the exact same proof, so I'm not going to repeat this, tells us how to expand E's and H's in terms of monomial symmetric functions. So these are the monomial expansions of the E's and the H's. So it says the following: if you want to expand E lambda in terms of the monomial symmetric functions m mu of x, then the coefficients are what we'll call n lambda mu. Okay, so this is now going to be, so let me say, let lambda be a partition of d. Okay, fix some d and I take partition of d. I look at the corresponding elementary symmetric function E lambda, and what is it equal to? Well, it is equal to n lambda mu m mu of x, where let's write the other one also. H lambda of x is m lambda mu. So we gave these names earlier also. M mu of x, mu running over partitions of d, where m's and n's are the sorts of things which appear in the RSK algorithm, the RSK correspondence, right? So what is m and n? Where m lambda mu is the number of integer matrices, non-negative integer matrices, Z plus matrices with row sum lambda, column sum mu. Okay, and n lambda mu is the same thing with 0, 1 matrices. So this is the number of matrices which only contain zeros and ones. Okay, not quite, so we need to be slightly careful here. So it's all 0, 1 matrices whose row sum is that's right, row sum lambda and column sum. Okay, now let's see what these have got to do with the RSK correspondence. So observe that RSK and dual RSK tell us the following. By RSK, we know that m lambda mu is, well, it's a number of number of Z plus matrices with this property, but this is just the same as the number of pairs PQ, right? This is just a cardinality of, because RSK is a bijection, I might as well count pairs PQ whose, well, what are they? I want them to be semi-standard Young tableau, the same shape, and whose types are the row and the column sums, right? So the row sum, remember, is in this case lambda, and the column sum is mu. So I just want to look for Okay, so we can actually think of these matrices as being of infinite order, infinite cross infinite if you want, but the actual action again is only finite, because lambda and mu are only finite. They're finite partitions, they have finitely many non-zero parts, so only finitely many rows and columns can possibly be non-zero. Okay, so this is really the set whose cardinality we are trying to count. So how are we going to do this? Well, this is just same thing as saying I don't know the shape, right? So the thing that's unknown here is the shape. So I will allow all possible shapes. So let's take all possible shapes nu, and it's enough to look at nu, which is a partition of D, right? Because that's the the total row sum lambda and mu are both partitions of D. So nu would also have to be a partition of D. And what do I need? I now need to look for all semi-standard tableau of shape nu and type lambda. So this is a cardinality of a set of semi-standard Young tableau whose shape is nu, type is lambda, times the same thing for mu, shape nu, type mu. Okay, and again this is something we have done before, so this is just all. This number is what's called k nu lambda, the Koska number. This is the Koska number k nu mu. Okay, so what we have just said is this fact that m lambda mu, the coefficient that appears when you expand when you expand the the h lambda in terms of the m mu's, the coefficient that you get are, those coefficients are just going to be the products k nu lambda times k nu mu. Now the dual RSK tells us a similar fact about n, and let me just write that down and you can sort of see how the proof goes. So this is now, since it's pairs of tableau rather than pairs of tableau of transpose shapes. So the shapes are nu and nu prime, and the column sum is lambda and the row sum is mu. Okay, so this is now going to count something slightly different. The shapes are nu prime and nu. Okay, so this is the key point. So this is what RSK gives us. It tells us how to expand the monomial in terms of monomials, the h lambdas and the e lambdas.